Okay, so in this lecture we will solve the diffusion equation in 1D using a very general approach. Okay, so the diffusion equation in one dimension is just dou p by dou t is equal to d times dou squared p by dou x squared, right? So the initial condition that we will choose is such that it will actually allow us to consider other kinds of initial conditions as well. We will come to that later on, but let's say that our particle is localized at the origin at time t equal to 0, right? So there is no chance for the particle to be found anywhere else at time t equal to 0. It's localized at the origin. Now as time, so we write this down as p of x comma 0 is equal to delta of x, right? So this is the density, probability density is just given by delta of x. Now as time progresses, we would expect that a wider and wider region of space is going to be covered, right? There's going to be a non-zero probability of finding the particle, and so we also impose these natural boundary conditions, which is very physical, right? So the probability of finding this particle goes to 0 as x tends to plus infinity or minus infinity, right? So as you go further and further away from the origin, the probability of finding this particle is going to be vanishingly small. So the time variable starts from 0, and the spatial variable also goes from minus infinity to plus infinity. So we will solve this problem by taking a Laplace transform with respect to time, which goes from where the variable t goes from 0 to infinity. So it's the Laplace transform is a suitable transform to take here. And on the other hand, with respect to the spatial variable, which goes from minus infinity to plus infinity, we'll take a Fourier transform, right? So let's start with finding the Laplace transform. We will denote this as PL of x comma s instead of from P of x comma t. So we take a look at this differential equation, and then when you take the Laplace transform, on the left hand side it becomes s times PL of x comma s minus this P of x comma 0, as we know from Laplace transform theory. And on the right hand side, it's just basically the same. In place of P of x comma t, we write it as PL of x comma s, right? It's just this function alone which is getting, whose Laplace transform is being taken. So it's just simply replacing by a different function here, and in place of t we have s here. Now P of x comma 0 is of course given to us to be just delta of x, right? So we can write this as s minus d times dou squared by dou x squared. PL of x comma s is equal to the initial condition, which is just delta of x. Now we want to take the Fourier transform of this function as well, and so it's convenient to actually write PL of x comma s in terms of its Fourier transform. So the relation that we're going to invoke here is actually the inverse Fourier transform. So PL of x comma s can be written as 1 over 2 pi integral minus infinity to plus infinity PLF of k comma s, so the e to the I kx dk, right? So PL of f is, it has both, where it's the function where both the Fourier and the Laplace transform has been carried out. So PL of x comma s can be replaced by this expression. So, and then we also use this integral representation for the delta function, which is simply given by this integral, right? So if we plug this stuff in, so we have on the left hand side s minus d times dou squared by dou x squared, PLF of k comma s, then e to the ikx is the same as e to the ikx, right? So we have compared the integrands on both sides, right? So this stuff has this integral, and then this stuff also has integral. So we can go ahead and write s plus dk squared PL of ks is equal to 1, right? So this is a simplification which ensues, and then we can go ahead and solve for PLF of k comma s, right? So this is immediately seen to be 1 over s plus d times k squared, right? So all we have done is some simple jugglery involving taking a Fourier transform and a Laplace transform, and then simply arguing that the integrands are the same, and then some simplification, and we immediately have s plus, I mean you take this derivative, so you get a k squared which comes in, and so s plus dk squared times this is equal to, you know, the e to the ikx can be removed, and this quantity is seen to be 1. So PLF of k comma s is equal to 1 over s plus dk squared. Now if you take the inverse Laplace transform of this function, which is straightforward to do, we get e to the minus dk squared t, and then we have to take the inverse Fourier transform of this function to get back p of x comma t. If you do this, so then you have this integral to be performed 1 over 2 pi integral from minus infinity to plus infinity e to the minus dk squared t e to the ikx dk, which returns to us this familiar Gaussian integral. So this is a Gaussian integral, and then you get a Gaussian as the final answer. So this is p of x comma t is equal to 1 over square root of 4 pi dt times e to the minus x squared by 4 dt. So this is a plausible result and something which is familiar, right? So we saw the discrete version which had this Gaussian appearance, and indeed the general solution also is Gaussian in nature, right? So initially our particle was localized at the origin, and then we see that the probability density keeps on spreading, and in fact a key point to notice here is the width, which is given by this variance. Variance goes as is linear in t, which is it's characteristic of diffusive motion, right? So what is called ballistic motion is characterized by, you know, the spread being proportional to time, whereas here it's the variance which is proportional to time, right? So in diffusive motion, if a walker takes n steps, you know, he's typically covered n steps, whereas in ballistic motion it covers steps which is proportional to n, whereas in diffusive motion n steps will probably give him only square root n, of order of square root n. So that's, you know, symptomatic of diffusion, and it holds in, you know, different dimensions, it holds in the continuous version, discrete version, and so on. Now we have solved this problem with some very specific kind of initial conditions, but this initial condition is a, you know, is such that it's amenable to generalization. So in fact, if we pause and think a little bit, what we have found is really what a Green's function, right? So we have worked out the solution for the delta function. So if you have some other initial condition, if your initial probability density is some p init of x, so we can just use the Green's function prescription and immediately write down a formal expression for the full solution. P of x comma t is going to be 1 over this, you know, this constant from minus infinity to plus infinity. Now we have to shift this e to the minus x prime of the whole square divided by 4 dt times this, right? So this comes about just from the Green's function theory, which we are familiar with. So the advantage with the initial condition we have considered here, we have worked out the full solution here, and therefore it automatically leads us to a more general solution, assuming these natural boundary conditions, which is that this probability must die down to 0 at plus x equal to plus and minus infinity. We look at, you know, some other interesting boundary conditions, and we will solve the same PDE by a different method in the lectures coming up. But that's all for this lecture. Thank you.